So today is going to be a bit of a technical session, really a programming session, because I'm going into advanced aspects of Palabos, about how to extend Palabos to implement your own models. So the topic of this morning are the data processing functionals, which are also called data processors in Palabos, which you use to implement anything that is not local collision models. For local collision models, you saw that you have to write a class which is of type dynamics, which implements the collision scheme. And for everything else, well, you have a framework of Palabos that is automatically parallel, that is called data processors. I'm going to introduce that today. You also have a PDF version of that presentation on the drive. And so, as I said, some aspects are a bit more technical. So I wrote more text than usual also on the slide, so that you can use these slides as a reference, as a text to go through if for your own research you want to implement data processes in Palabos. But before going into these details, let me remind you of the concepts, the programming model of Palabos, which I presented yesterday morning. There are three ways in which you can extend Palabos and write your own models. The first are lattice descriptors. The data structure on which you work when you run the Palabos simulation are multi-block lattices. They allocate data. And you can define how much data they allocate, how many populations, how much data additionally to these populations by writing a lattice descriptor. The lattice descriptor also describes the connectivity between cells and their neighbors and describes how data is moved during the streaming step. Then you have the dynamics objects through which you can implement a collision model, which means when you use Palabos fundamental collision streaming scheme, you can describe with these objects in which way every single cell implements the collision. And now the third part, that's the data processors, that's today's topics. Those are for everything else. So everything else, everything which does not fit into the two first topics goes into data processors. To give you a few examples of data processors which exist in Palabos. So you can have a data processor to couple with other types of solvers. For example, if you have a coupled problem and part of the problem is solved with lattice Boltzmann and part of the problem is solved with a finite difference scheme, then, well, you get data from the finite difference scheme, which you can couple back to the Palabos solver through a data processor. Data processors are also the mechanism you are going to use most likely when you have multi-phase models. For example, there is a volume of fluid multi-phase model in Palabos, which uses a whole sequence of data processors. It is used in diffuse interface multi-phase models. So, for example, in the pseudo-potential model, the Shan-Chen model, which is implemented, which uses, well, two or multiple species, each implemented through its own block lattice, and those block lattices are coupled with each other through a data processor. You are going to use them to implement non-local boundary conditions as the ones Francesco introduced yesterday afternoon. They are used to compute integral quantities. If you have a simulation and want to sum or compute the average of a quantity like the pressure, the energy over the full domain, this is obviously a non-local operation. From a computing standpoint, you talk about the reductions. Well, data processors do that for you too. And well, general algorithms which have nothing to do with lattice Boltzmann, parallel algorithms are often implemented with data processors because they are a convenient framework for doing so. For example, you have in Palabos something which is called the voxelizer. When you provide a geometry, the geometry of an artery, to take an example from yesterday, for example, and want to compute which cells are inside the geometry and which are outside, an algorithm called the voxelizer is doing that for you with parallel efficiency because it is implemented through a data processor. So we call them data processing functionals and data processors for short. They are the realization of a data parallel paradigm. That means you have your data sets, which are scalar fields, vector fields, block lattices, and there's an operation which you would like to execute in a data parallel manner. So those fields are distributed over many cores of a computer, and you want every core to do the same thing on a different part of this data set. That's what the data processor is doing. We use it for everything which is non-local, because for local operations, implementing a new collation scheme is more efficient. They work on lattices, scalar fields, and tensor fields, and they can also create couplings between different types of fields. For example, and this is going to be, well, in the exercise today, we're going to create a coupling between two different types of lattices, but you can also, for example, get the data from a scalar field and use it on the cells of a lattice by explicitly creating a coupling through a data processor. As I said before, they also perform parallel reduction operations. So to understand a little bit this philosophy of the data processors, you have to understand that I will just get a little bit rid of these commands of Zoom, sorry, to see my screen a bit better. There we go. So we are in the context of having to execute an operation on all cells of a data structure, which is like a matrix. Now in Palabos, this matrix, which we call the block, is subdivided into smaller components, which we call the atomic blocks. And those components are distributed over the nodes of a parallel machine. So the original loop which you have, which processes all elements of the matrix and does the same operation over and over again, is in reality split into many loops. One loop for each of these atomic blocks. A given node of the parallel computer can have one atomic block or many, so it can execute one loop or many loops. The trick is that you don't want yourself to write many loops, especially that all of them are doing the same. You want to write one generic version of this loop, and you want Palabos to execute that loop many times, once for every one of these atomic blocks. And this is what the data processors do for you in a transparent way. You remember this decomposition of your domain into atomic blocks, and I showed you an example of how this decomposition could look like. So you have a domain, the full domain is our multi-block, which is in this example split into 3 blocks, the atomic blocks, which we call A, B, and C. So these blocks, but they don't overlap, okay? They join to create the full domain of the multi-block. But additionally to covering the actual domain of the simulation, we extend each one of these atomic blocks by an additional layer which we call the envelope. And this envelope is just, well, an enlargement of the atomic blocks, which is created for the purpose of communication. This is how, well, within one multi-block, cells communicate with each other. And this is a mechanism you need to understand, because as you are implementing your data processors, you need to understand when you write the loop over one part, one domain of the full domain, how you access neighboring data. These envelopes, I show you again a similar simulation, this time a bit more schematic. And this time, in this case now, the full domain is a square, and it has been split into 4 atomic blocks, all of which have the same size. Okay, so you see from left to right how the full multi-block is split into 4 atomic blocks. And in this example, you see the individual cells. Each atomic block has an additional envelope, in this case, of 1 cell thickness. It can be more than 1, it can be 2 or 3 cell thickness. This is something the user can choose. And these envelopes are ghost cells. They correspond to an actual bulk cell of another atomic block. If you take, for example, the cell which is highlighted in black on this scheme, you see on the left that this cell, well, is a cell of the original multi-block, and it belongs to the atomic block which is on the top left of the domain. Now, this cell is going to exist twice, which means the value of the cell is going to be copied into the envelope of the atomic block, which is the top right one. So this is a mechanism that is implemented by Palabos. Automatically, well, the value of this bulk cell is computed by a given algorithm on the top left atomic block, and Palabos implements an automatic communication mechanism to produce a copy of that value inside the envelope of the top right atomic block. So parallelism works in that way. When you execute an algorithm, for example, on the top right atomic block, you can expect that you can access some sort of neighboring data depending on the thickness of the envelope, which has been updated with the proper values by a mechanism belonging to Palabos. So this is the idea of these envelopes. Then I will show you how you actually write the data processor. So far, does anyone have questions? Does anyone have questions? As yesterday, don't hesitate with the questions. You just unmute your microphone and start talking without raising your hand. There is no problem. The session is recorded though, and the non-recorded question session is happening at the end. The example with which you will be working in the exercise this morning is an example of a coupling between a fluid and a scalar field. The scalar field, we're not going to say what it is. It could be the temperature, it could be a chemical species. It will be something which we call C. So C is a scalar value which follows an advection diffusion equation. On the top part of the screen, you see, well, the incompressible Navier-Stokes equations. So the momentum equation on top and the continuity equation on bottom. This one we are going to solve through BGK lattice-Boltzmann scheme. And on the bottom, you have the advection diffusion equation for our species C, which is advected with a velocity u that comes from the Navier-Stokes equation. So that's where the coupling comes in. The fluid equation is going, the fluid velocity is going to advect the scalar species C. So we're going to solve that one, the advection diffusion equation, through lattice-Boltzmann as well, also with a BGK scheme, and write a data processor that transfers the velocity from the Navier-Stokes equations to the advection diffusion equation. To do this, we will need 2 lattices because, well, we have to solve 2 equations, and also because the data allocated for every one of these is not the same. For the fluid, we are going to use D3Q19. Actually, in the examples, we are going to move to a 2D case because I find it easier to quickly have results and look at them in a 2D case. But if it is 3D, well, you use D3Q19, which is a classical choice for incompressible Navier-Stokes through lattice-Boltzmann. And for advection diffusion, D3Q7, because you can solve that equation with fewer degrees of freedom. and then instantiate one lattice for the fluid, one lattice for the advection diffusion equation, everyone with its own descriptor. Now, the idea of the data processing functional, which is going to instantiate the coupling between these two lattices, is the following. So, when you write a data processor, you write a function which, when it is executed, receives as an argument two lattices. And then, well, it writes an explicit loop inside that data processor to parse the data of a domain of these two lattices. It goes to one of the two, the fluid lattice, computes the velocity, and copies that velocity over to the other lattice, the advection diffusion lattice. To tell Palabos what is going on, your class, which has this method, this function, needs to inherit from a specific class that tells Palabos what is going on. So it inherits from a canonical processing functional class in Palabos, and there are many of them. So you have to instantiate one of these classes to tell Palabos what is going on and to add your own methods. These methods are virtual functions which are overridden to specify the specific behavior of your data processor. In this case, the name of the class from which you are going to inherit to write your own data processor is called the box processing functional 3D underscore LL. Box means that it is applied to a rectangular domain. Processing functional means it is a data processor. 3D means, well, it is in 3D. And LL means lattice. It is a data processor which is applied to two lattices. There are many other data processor, canonical data processors from which you can inherit. There is some of them which take a scalar field as an argument, or a tensor field, or a mixture of lattice and scalar field, and so on. There are some of them which are called reductive box processing functional, which are for specific data processors that execute reductions. So on top of everything you are doing, you may want to tell Palabos that at the end of the execution of your data processor, a global reduction operation must be carried out, for example, to compute a global sum or a global average or minimum or a maximum over the domain on which the data processor was executed. So I'm now switching to 2D because the exercise is going to be 2D. This is the declaration of the data processor of this exercise, the exact code. This is how it looks like. This is again a template, okay, like everything in Palabos which is generic. It is a bit of a complex template because it works on two lattices, each of which has its own descriptor. So you are going to say that there is a generic type T, which is the floating point type, double precision or single precision. And then there is a descriptor for the first lattice and a descriptor for the second lattice. And there are four methods inside this class. Or maybe let me say first that this class inherits, as I said before, from a box processing functional 2D underscore LL, where LL says that this is a data processor that works on two lattices. Then there is a constructor which is empty in this case because the class has no data. There is the most important method which is called processor. This is the method in which you are going to write your algorithm. This is the data processor. You see that it has three arguments. One is a domain, one is the fluid lattice, and one is the scalar lattice. This domain argument is crucial, and I'm coming back to that. This is not the domain on which the full data processor is executed. This is the smaller domain. Once Palabos has split the full domain into smaller domains on which the algorithm is going to be executed, it provides that smaller domain to the data processor or to the process method. Then there is a function which is called clone, and I will come back to that one. And there is one which is called the getTypeOfModification. I will go now step by step through these through three methods because the constructor is just empty. The clone function is a technical function which you meet very often in Palabos. Essentially, all classes have a clone method which tells Palabos how to create a clone of a given object of that class. That means Palabos is capable to take whatever classes you provide to it and during runtime clone them, create an exact copy of these objects. In other programming languages, you have built-in mechanisms to do so. In C++, you have not. And to extend well the capabilities of C++, Palabos expects from the user to implement a clone function for every class. Clone functions always look the same. They always look like the clone function you have on this screen, and it is a very technical aspect of Palabos. You are essentially going to copy-paste that one whenever you implement your own data processor. To create its dynamic clone of a given object, this method just uses the copy constructor of that class, which means that now I'm going a little bit into C++ details of this whole thing, which means that you also need, as you always should, to implement a proper copy constructor for every one of the classes you have. Then there is that method which is called getTypeOfModification, where you tell Palabos what kind of data was affected by your data processor. And this information is going to be used by Palabos to decide what kind of MPI communication to instantiate. Because you remember that there is this concept of envelopes. So every multi-block is split into atomic blocks, and the atomic blocks have envelopes, and they are updated through MPI communication by Palabos. Now, if your data processor does nothing, Palabos does not need to instantiate any communication. If you change one of the two lattices, then communication must be instantiated only for that lattice, and if you change both, then communication is needed for both. So these, well, Palabos cannot, analyze your code and understand what's going on, so that's something you are going to tell in this method, getTypeOfModification. As you can see here, we say that the first block was not modified by providing the constant nothing, and the second one had its static variables modified. Static variables is essentially the populations plus some additional data which is potentially stored right after the populations. I'm going to tell you exactly which constants you can use in this context and what meaning they have. So when you implement getTypeOfModification, you're going to indicate for every one of the lattices which are provided as an argument. In this case, there are two. There is the fluid and the advection diffusion. We are not going to modify the fluid. We are just going to copy the velocity of the fluid to the advection diffusion, which is why we say nothing has been changed for the fluid, but static variables, the velocity that is stored right after the populations of the advection diffusion field is changed. That's where the constant static variables is used. You also have a keyword for dynamic variables. This is when the data processor changes the content of the dynamics object. The dynamics object, which specifies the collision scheme. For example, the dynamics object could be BGK dynamics, which it was in the default example provided yesterday. So these dynamics objects, they are general classes which can have their own data, and these data can be changed by the data processor. For example, BGK dynamics contains the relaxation time of the local collision. So in every cell, you have a different dynamics object, and every one of these dynamics objects can have its own relaxation time. It is possible that your data processor parses the cells, accesses the dynamics objects, and changes their relaxation time. In this case, you need to tell Palabos that the dynamics objects have changed. Palabos is then going to access their data of the dynamics object and send it through MPI to the other processors to update the dynamics objects properly inside the envelopes of the atomic blocks. Then there's a keyword that is called all variables if you change both static and dynamic content. And then there is one which is called data structure. If you do, that's the worst case scenario. If you do not only change the data of the dynamics object, but replace them by another one. Imagine that you have a data processor that goes through your lattice and says, well, on this cell, I'm going to replace BGK by bounce back, or I'm going to replace a BGK by recursive regularized dynamics or something else. Then you have to tell through the keyword data structure that you did so to Palabos. And Palabos is actually going to go to that cell and serialize the dynamics object. So it is going to convert the full dynamics object into a data stream, which it sends to MPI to the envelope or on a different processor and rebuilds the full object on a different processor, okay? So these are the keywords which you are going to use inside the method getTypeOfModification. Let's take a small break to see if anyone has a question so far. I understand that all of this is a bit abstract, obviously, but I'm still going through all aspects of the data processor so that you have the information somewhere, and then everything is also clarified when you go through the exercise afterwards. Let me take just a short moment to be sure that everyone is still with me. Or no, let's do it differently. Could just everyone, somebody take tell me that you are still hearing me?
We do hear you.
Okay,
Yes.
thank you. Thank you very much. Now let's go to the implementation part of that data processor. So that's how to write the process method. As I told you, you are going to write an algorithm that says what to do on every cell of your multi-block. And Palabos is going to split the domain, the application domain of the data processor into smaller domains. Now these smaller domains, they can have very unexpected shapes, because what happens behind the scenes is that you are going to do a coupling between a multi-block A and a multi-block B, but maybe they are not subdivided in the same manner into atomic blocks. They have maybe different subdivisions. So what Palabos really is going to do, it is going to take the atomic blocks of those fields and search for overlaps. And all these overlaps are rectangular domains for which Palabos calls the data processor ones. So it is going to compute these smaller domains, which I'm going to call the domain argument, and provide them to your process method with the corresponding atomic blocks A and B to ask your data processor to execute, to carry out a loop on this smaller subdomain. So we are going to write a method which receives a domain with coordinates, well, in 3D, x0, x1, y0, y1, z0, z1. And you are going to write a loop which goes over the two atomic blocks which you received as an argument. As an argument, you have a domain, an atomic block A and an atomic block B, and you are going to write a loop over the two atomic blocks. The problem is that the coordinates are not the same on those atomic blocks, because as you saw in the slide before, these two atomic blocks, they can have a completely different layout in memory. They can even have different types of envelopes. So the domain argument, which is provided to you by Palabos, is providing you the coordinates relative to the first atomic block, the very first argument you received in this data processor. And the coordinates in the second atomic block, they are shifted. So you are going to ask Palabos to provide you with the relative offset of coordinates between the two atomic blocks, compute relative displacement between A1 and A2, and you are going to add that offset to access the data of the second one. Okay. And then these coordinates are local coordinates of these atomic blocks. They are not the global coordinates within the multi-block. So imagine that your data processor needs to know the global position because it wants to have absolute values. For example, imagine that you are implementing a force field, which is a gravitational a great gravitational force over your domain, and then there is a gradient in this force somewhere. Okay, then you need to know where at which height you are to apply the proper value within your gradient. And in this case, you need to convert your local coordinate to the global one to know where you are. And then there is a function provided by Palabos, which is called getLocation, which again provides an offset to you, which implements that translation from local to global coordinates. So this is actually the full code of the process function. So the first part of the exercise will be very easy. I just provide the code to you in this slide, and you're just going to write it into the code. Okay, this is going to be copy paste, but I think it is a necessity to write the stuff once to see how it works. So you see, we are back to our process function, which receives 3 arguments. The first is the domain, which has been computed by Palabos and provided to you, where Palabos says, well, please parse this domain and implement your operation on this domain. The first is the fluid lattice, then comes the fluid lattice, and then comes the scalar lattice. We want to parse the fluid lattice to compute the velocity on every cell, and then we are going to copy it to the scale to the lattice, which is computing the advection diffusion equation. So the lattice which computes the advection diffusion equation is also a lattice, Boltzmann lattice. It has populations. But after all the populations, so I think that in 2D this is going to be 5 populations, it also stores the velocity. So every cell has essentially in 2D 7 values, where 5 are for the populations and 2 are for the velocity. So we are going to write the fluid velocity into these 2 velocity values, and then the local collision step is going to use them to compute the equilibrium and implement the lattice Boltzmann scheme. The first line of this data processor is going to access the descriptor of the advection diffusion field to determine at which position inside the cell the data of the velocity is being stored, so we can write it into this. Then, as I said before, we need to compute the relative offset between the fluid lattice and the advection diffusion lattice to be able to access their coordinates. Then you as a user have to write an explicit loop over the domain provided to you by Palabos. In this loop, you are going to compute the velocity on the fluid field. So that's the line which says fluid.get ix iy, because ix and iy are the coordinates of the fluid lattice. Fluid.get gives you a reference to the cell at coordinates ix iy, which has a method compute velocity to compute the velocity. And once you have computed that velocity, you can copy the velocity to the advection diffusion lattice into its scalar field, scalar extension that comes right after the populations. This is now a data processor that implements a coupling that uses functionalities of cells on either side on both lattices and copies data from one to the other. This data processor is fully local because you never I mean, none of the cells needs to access neighboring cells, but because it involves a coupling between two lattices, you cannot implement it in terms of a local collision. You cannot have a dynamics object which is doing this operation, although it is local, because it has two arguments. It has also the capability to be non-local. So as you play with this code, you can try it out. Depending on the envelope instantiated by the multi-block lattice, every cell can also access neighbors. In the example we will provide to you, the envelope is of size 1. So every cell, every lattice here has the possibility to have read access to one of its neighbors. Okay. Does anyone have questions about that code we are looking at right now? When you implement data processing functionals, you have to follow a set of rules. If you do not follow them, you will have errors of parallelism, which means that the parallel program is not going to have the same results as the non-parallel version.
Jonas, I have a question. Maybe. In the last slide, you did this loop and this computation on atomic block, yeah, or envelope.
That's on, yes, on the bulk of atomic blocks, yes.
Atom. And how you want to do some computation on envelope, because in envelope we have some overlap. So when in the overlap we are doing computational twice, maybe, because one from this from the atomic block A and another one in atomic block B. And
no, so the idea is that the computation is not going to be done twice. It is only going to be done once. But at the end of the computation, the result of your computation is going to be copied into the envelope, so they are available for the next computation. So essentially, you see here, Palabos gives you a domain argument, and this domain argument does not contain the envelope. It only contains the bulk. So your loop is only going to loop over the bulk, as we see it in this sketch here. So the domain argument which Palabos provides to you corresponds to the gray area on the picture on the left. And this gray area does not contain the envelope. So your data processor only works on the bulk. Well, it only writes into the bulk, but it can read from the envelope. And it has the guarantee that the data which it reads from the envelope is correct, because the envelope has previously been updated by Palabos. Okay?
Thank you.
You're welcome. So you are writing data processors which have to act on the full subdomain of all atomic blocks which Palabos has provided to it. Now, the subdomain, that's the domain argument which Palabos gives you, defines the area in which you can write. You are allowed to write only into the area of the subdomain provided by Palabos. But you can reach outside this domain through read accesses. You are allowed to read data outside of the provided domain within the reach of the envelope. If the envelope is 1, you can do read accesses outside the domain by an extent of 1. If the envelope is 2, then you have a reach of 2. But outside the subdomain, you cannot have write accesses, you can have read accesses. If you write outside the domain, essentially what you are doing will have no effect, because your data is going to be erased by the subsequent communication process of Palabos. Now, the operation which you perform can be space dependent. What does that mean? You can do an operation which depends on the explicit value of the x and y coordinates. That was not the case of the example of the previous slide. when you wrote the coupling, well, we did not use the X and Y values explicitly for our computation. We just took one cell, computed the velocity, and copied and put the result in the other cells. If you want to use the X and Y coordinates explicitly, you can, but you have to convert them to absolute coordinates. If you use if you use the local coordinates, the result is going to be wrong. I would say that a mathematician would formulate the same sentence as follows. When you write a data processor, it must be written in such a way that executing your loop, your data processor, once over a given domain must have the same effect as splitting that domain into subdomains and then executing that loop consecutively on each of these subdomains. This is exactly what is going to happen, because Palabos is splitting the full domain into subdomain and then is executing your data processor many times subsequently. Okay, if you understand these rules and if you follow these rules, all your data processors are going to work fine. And you do not need to care about issues of parallelism, because parallelism is taken care of by Palabos. Any question? Now, once you have written a data processor, it needs to be executed. There are two mechanisms for that. Either you can execute the processor just once manually, or you can have it executed automatically at every collision streaming cycle of your model. In this case, we talk about internal data processors. That means that the data processor can be attached to a multi-block. And once it is attached to the multi-block, it can be executed as many times as you want within the execution of the collision streaming cycles. If you want to execute your data processor just once, you call a function that's called apply processing functional. You provide the name of the data processor while you create an object of your data processor. You provide the size of the global domain on which the data processor is going to be executed. So the global domain, which is going to be split into smaller domains by Palabos. Then you provide the arguments, as many multi-blocks as you wish, which are going to be split into atomic blocks and subdomains and provided to the data processor for its execution. Apply processing functional is what you are going to use if you call your data processor only once or only a couple of times. Apply processing functional is a little bit slow because, well, when it is executed, Palabos needs to, do this decomposition and computation of the smaller subdomains, which takes a little bit of time. If your data processor is going to be executed at every cycle, you're going to want to use the second mechanism, which I present in the second slide, which computes the subdomains only once and then executes fast. So the second command which I'm teaching you is integrate processing functional. It has essentially the same arguments as apply processing functional, but it just attaches your data processor to a multi-block. And then you can call it, execute it through this multi-block. There is one additional argument to integrate processing functional, which is called level. This is the processor level at which it is attached to a multi-block. The level can be understood as a group. In practice, you may have many data processors and you want to group them together. So there is the group of level 0, the group of level 1, the group of level 2, and so on. And the reason for this grouping is that the communication, MPI communication, is going to happen between groups. So Palabos is going to execute all data processors of group 0. Then it will check which data you have modified because you have told Palabos so through the method getTypeOfModification, and it will update the envelopes correspondingly. Then it executes the data processor of level 1, it updates again the envelopes, and then the groups of level 2, and so on. So the reason for having these groups again is not to have too much communication when it is not needed. You will yourself know when you require communication or not. So within one group, you will do independent operations which do not require non-local information from each other, because communication is not going to happen within that group. Then communication happens, and then the next group is going to be executed. Now, once you have attached a data processor to multi-block through the function integrate coprocessing functional, you can call it manually by calling the function execute internal processors on a multi-block, or you can have it executed automatically, which happens through the collide and stream cycles of a multi-block. This is what is happening in the exercise which we provide to you. As I said, processor levels are counted from 0 upwards. Inside a processor level, the data processors are executed in the same order in which they were added, attached to the multi-block. Then communication, which is the update of envelopes, is performed after execution of data processes with write access only when you switch from one processor level to the next. Now, processor levels, they can have positive or negative values. They can be 0, 1, 2, 3, 4, 5, that's positive, or they can be -1, -2, -3, that's negative. The reason for that is that we want to make the difference between data processors that are executed automatically during the collision streaming cycles and the ones which are not. So during collision and streaming cycles, Palabos will parse all the data processors that are positive processor levels and execute them automatically, but not negative ones. That's the ones you want to only be able to execute manually. Those you will execute manually by calling the method execute internal processors of the multi-block and provide as an argument the processor level at which you want the processes to be executed. Okay, again, all of this is a little bit abstract, and I made sure to write full sentences on the slides. So later on, when you are implementing your own data processors and want to remember how the stuff works, you can reread the slides again. This concludes the general introduction to data processors. I'm then switching to a last topic, which are the reductive data processors, but it gives you all the data you need to carry out the exercise. Is there any questions so far?
Jonas, could you please repeat the concept of levels, please?
Yes. So levels must be understood as groups. When you write a physical model, you usually write many data processors, not only one. For example, when we wrote the volume of fluid free surface method, there are many data processors. There is one which is maybe advecting mass. There is one which is implementing the physics of the surface. There is one which is implementing a force term. There are many data processors which we want to be executed in a given sequence. So you can think that you just attach all these data processors to a multi-block and then they are executed in that same sequence. But the problem is that if we did so, usually too much communication would be happening, too much MPI communication. And MPI communication is expensive. When you write these data processors, you know that sometimes you need the communication and sometimes you don't. So this is why we do the grouping. The reason that we group the data processors is to tell Palabos that we want communication to happen only from one to the next group. So essentially, imagine that you have data processor, which we will number from 0 to 10. And you know that if the first 3 data processors, they don't need data from each other. So you are going to say that, well, let's put data processors 0, 1, 2, 3. Let's put them in group 0. Then Palabos is going to execute them because they are in group 0 first, and then Palabos is going to do communication. Then come data processor 4, 5, 6, which you put in group 1, which are going to be executed afterwards. And after the execution of all data processors of group 1, Palabos is going to do MPI communication again, and then comes group 2. Okay, so the levels, which are numbered 0, 1, 2, 3, are groups to which every data processor is assigned. These levels have two meanings. First of all, they decide the order of execution, because data processors from group 0, from level 0, are executed before the ones of level 1. And second, they determine when communication happens, because communication happens when you switch from one level to the next one. Does this answer your question?
That's perfectly clear. Thanks.
You're welcome. Is there any other question? Then I will just switch to the final topic, which is reductive data processors. Now, reductive data processors are normal data processors. Whatever you do in a data processor, you can also do it in a reductive one. But it has additional capabilities, which is to compute global reductions. For example, a sum over values which are attached to every cell. To show you how that works, I will just show you the implementation of a data processor that exists in Palabos, which computes the average values of all the cells in a scalar field. So you have a scalar field C, which has n cells, and you want just to compute C average, which is the sum over all cells of Ci divided by the number of cells. To do this, this is a program you would write in an end user code of Palabos. Compute average takes a multi-scalar field, the domain, the global domain on which you want to compute the sum. You will instantiate an object of type box scalar sum functional 3D, which is predefined in Palabos. You will apply it. You will apply this data processor to your scalar field on the global domain. And then this functional is still available, and you call its method getSumScalar to access the sum which has been computed. And in the end, you divide it by the number of cells in the domain. For this, you do need special data processors, because it is impossible for you to do this manually. Because manually, well, you understand that to compute a global sum over the full domain, which is split over many cores of a parallel machine, you need MPI communication, you need an MPI reduction. But this MPI reduction, you cannot do it yourself, because you don't need how the domain has been split by Palabos. So somehow you need Palabos to call these MPI reduction functions for you. And the mechanism, the abstraction provided to you by Palabos to do so are the reductive data processors. Now, this box scalar sum functional exists in Palabos, but I will show you the code so you understand how you can yourself write your own reductions. This is the declaration of this box scalar sum functional 3D. Like every data processor, it inherits from a canonical data processor of Palabos, which in this case is called the reductive box processing functional 3D underscore S. S stands for scalar, because this data processor takes only one argument, which is a scalar field. And then we have the usual methods: the constructor, the process functional, the clone function, the method getTypeOfModification. Additionally to a conventional data processor, this data processor has data. It is an integer valued variable, which is an identifier for Palabos of the sum you are going to compute. Because within a data processor, you might want to do many reductions, maybe 2 sums, 1 maximum, 1 minimum. Those reductions are going to be computed by Palabos, but they need to be identified through an integer identifier. So this tag is something you have to store inside your class. This is the process function. As usual, you just write a loop over the full domain. Here I provide the 3D case. So this is a triple loop over the domain provided by Palabos. You access the value of the scalar field through the function scalarfield.get. And then you want the reduction to be carried out by Palabos because it needs somehow to be properly done in parallel. So instead of making a manual sum, you call the method getSum on an object, which is the statistics object provided by you by Palabos. Palabos, as you do the sum, needs to know which one you are going to do if you have multiple reductions. So here is where you provide the identifier of your given reduction to that statistic. The identifier of this of your reduction is provided to you in the constructor. So you see here first the declaration of your constructor, where you access again the statistics object like before to subscribe a reduction. So as essentially subscribe sum tells the statistics object that this data processor is to compute one sum, and Palabos provides you an identifier through which you can actually. Additionally to sums, as I told you, you can compute minima and maxima. Okay. Now, just for convenience, this class also implements an access method getSumScalar, which accesses the computed sum. This method accesses the statistics object and its method getSum with the provided identifier to return the proper value. Okay. If you search a little bit through Palabos, you will find, many examples of data processors, reductive data processors, which also show you how things work. Do you have any question about reductive data processors? If not, let's see what you're going to do for your exercise this morning after the correction of yesterday's exercise by Francesco. We provided a code to you, which is in the drive, in the directory, in the folder Thursday morning, which solves again the 2D cavity flow, which we worked on yesterday morning. Now, additionally to solving the float field in the cavity, we also solve an advection diffusion equation in the same cavity with the velocity from the Navier-Stokes solver. This coupling will be done by the class velocity coupling 2D, which I presented in these slides, but we left the process function empty so that essentially you rewrite it based on the indications of my slides to make this code work. Then you can execute the code and look at the results and see how the advection diffusion field is entrained by the velocity field. Now, the third assignment is, can you make the interface of the scalar field sharper? So you will see that the scalar field is following the motion of the fluid velocity, but it also diffuses. So this assignment is to make the scalar field less diffusive to have a sharper interface. Now, the mechanism for the execution of this coupling is that it was integrated into the advection diffusion lattice to be executed automatically in the collision streaming cycles of the advection diffusion lattice. Instead of that, I encourage you to replace the integrate processing function by an apply processing function, which you will manually call within the time loop of this program at every iteration. So you play with the two available mechanisms. And that's the end of the exercise. We will not have a long exercise sessions, but I can give you a few hints of things you could play with this code. So a good thing if you want to practice data processors is to make the coupling reductive and then access something like the sum of the values of the scalar field. This you can do, you have manually called the data processor through apply processing functional. And you will see that although the velocity field has a boundary condition, we gave no boundary condition to the advection diffusion field. So the advection diffusion field is just periodic, which then looks a little bit strange because the velocity is confined in a box, but the scalar field is not. So you could add boundary conditions to the scalar field, and to see how to do that, you can get inspiration from a Palabos example, which is the Boussinesq thermal 2D example, which uses advection diffusion to model temperature. Okay, but I think you will not have time to do those this morning, so it would more be like assignment 1 to 4 to be executed that morning.